Good morning, everyone. Hello, 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 hello. Welcome to this, your favorite class in your favorite semester of your favorite year of your favorite degree. How are y'all doing today? Hopefully everybody's having a non-Garfield-esque Monday today. I know that the weather has been kind of a little bit, that's working. The weather is a little bit gross today. We had sleet this morning, but, you know, generally speaking, looks like the sun might be peeking around those clouds today, and we might end up with a nice day after all. So, how's everybody doing today? How was the test? Did you guys have a good time with the test? Hopefully it wasn't too bad. I was just gonna quickly look up the statistics on the test, but I should probably... Nope, doesn't look like the marks are in yet, so so it goes. So it goes. We will have to wait until probably Tuesday. I think they'd usually do it on Tuesday. Anyway. But yeah, I would be interested in your subjective impressions of how the test went. Can I go over how to do the bonus question from A4 or recursively? Nope, I gotta do my lecture material. However, it's sunny in Nova Scotia. Well, thank God for small miracles, because God knows Nova Scotia could use as much sun as it could get. What with being on the cold side of the Atlantic and all of that. The test was way too hard. Oh. Well, the test was harder than the first one, but, you know, it had to be, because the material's harder than the first one. It's like, you know, for the first one, all I could really test you on was, like, do you know what an if statement is? Do you know what a loop is? But, Oh, that's interesting, because I actually had pegged this test as being pretty, like... This one was easier relative to the one I gave last semester. The second test last semester, so... Okay. We shall see. Is my camera frozen, or am I just... Okay, I'm not frozen. Okay. People thought the test was hard. Okay. Well, if it's too easy, then you're not learning anything, I suppose. So, alright. Let's continue. So, lots of tears in the chat. Well, you know. Good. I was actually gonna throw a couple more questions on it, and I was like, that maybe not. Maybe I'll make it a little easier on them. So, perhaps you guys are glad that I didn't throw those extra questions on it that I was going to. So, anyway. We need to get through some material. We are talking today about numerical computations. Fundamentally, what we're talking about is the manner in which numbers are represented at the binary level inside of your computer system. So, we were started on this last time. We were talking about the manner in which binary numbers are represented, and mechanisms for converting between decimal and binary. It's, essentially, just to remind anybody who hadn't seen it already, when you're talking in binary, every 1 and 0, you probably have seen numbers encoded as 1s and 0s so far. Every 1 and every 0 is multiplied by a relevant power of 2 in order to create the number that is being represented. This is similar to how in decimal notation, you multiply by a relevant power of 10. So, we went over some conversion algorithms there. And so that's not the only ones that are relevant within the context of computing. Octal you won't see very often, but it is sometimes present. Hexadecimal is more common. It's unlikely that you will see much of either of these unless you go on in computing. However, it is still relevant for you to know what a hexadecimal and an octal number is. As the names would suggest, octal is base 8, and hexadecimal is base 16. So the reason why these are used inside of computing is that both 8 and 16 are, of course, they're base 2 numbers, right? 8 is 2 to the power of 3, and 16 is 2 to the power of 4. So, I think... Wait, am I getting that right? Man, it is a Monday morning. Yeah, because it takes 4 bits to represent 16, right? So that's like the underlying conversion here, is when you're talking about an octal number, you are talking about a number that may be represented in precisely 3 bits. And when you're talking about a hexadecimal number, you're talking about a number that can be represented with precisely 4 bits. The interesting thing about decimal numbers is it takes 4 bits to represent a decimal number, but some of the bit space is wasted, right? So, just loading up the Python interpreter. If we have something like, 1000, that's 8, right? And if you throw a 1 in there, that's 10. But 10 isn't a decimal digit, right? So going from 0 to 9, you're hitting binary numbers from 0000 to 1001. So if you wanted to represent decimal digits consecutively in memory, natively as decimal digits, you would be wasting a lot of space, right? Because these guys actually go up to 15, right? So that's, so basically you're wasting 10, 11, 12, 13, 14, and 15. Those 6 places within the number system, that it's not allocated to anything if everything was represented natively in decimal. So that's why we represent things natively in binary. So the thing is, with hexadecimal, essentially what you do is you map 10, 11, 12, 13, 14, and 15 to letters instead of numbers. Obviously, these are numbers above 10, so there's no single digit inside of the decimal system with which we can represent them. So we borrow letters. So if you want to write a hexadecimal number, you use 0x, x for hex. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15, and there's nothing higher than F. That's invalid syntax. So, so why? Why would we want to do this versus just representing things in binary? Sometimes binary numbers can get really long. Like, representing something in binary, it gets very long to represent a certain, number. Think about it this way. In order to represent 64 bits worth of memory, which is the standard size for things like floating points and integers in certain situations, you need 64 bits of memory in order to represent that. And because it's if you're working in binary, you're working with 1 and 0 values directly, which means you need 64 1s and 0s in order to be able to represent that number. Contrast that with hexadecimal. If you use hexadecimal to represent 4 bits with every character, then you only need 1/4 of the number of characters to represent the number. So, you know, instead of using 64 bits, you can use 16 bits to represent the same number, and that's much, much more efficient. Octal is a little bit more... one of the reasons it's more rare is because normally within computer systems we like bases of 2, right? Hexadecimal works really nice because not only is it representing a base 2 number, base 2 number of place values, it's also itself a base 2 number of bits, which means it aligns into computer memory much more easily. Octal being 3 numbers, 3 binary digits. These guys don't fit quite so well in along byte lines inside of memory. It's a little difficult to explain, but it has to do with the way in which memory is addressed. So, because this is the case, octal is not... You don't see it as frequently, but it does come up every once in a while. Normally in the context of legacy systems that were so... Like, memory used to be so expensive that, you know, octal representations were a thing. Like, if you could get away with representing something with 3 bits instead of 4 bits, that you would do that because memory was the expensive thing. Memory used to be the limiting factor of a computer system. These days, memory is very, very cheap. And the thing that's the limiting factor in a computer system is typically the CPU, like raw processing time. Normally, right now, clock speed is your CPU clock speed is the limiting factor on how fast your computer can run, not the amount of available memory. However, we must not forget that there was a time when a person's home computer system had a amount of memory that would have been measured in kilobytes rather than gigabytes. So, you know, at any rate, those are your other bases. I will now see if there are any questions. All right. Cool. So, all right. So now we've talked about the integers, and integers are easy, right? It's just straight representation of conversion from decimal into binary. You're done. It gets a little bit more complicated when you start talking about negative numbers and like 2's complement, but that's beyond the scope of this course. All you need to know at this point is if you want to represent a negative integer, it gets a little more complicated than just straight interpretation. But that's, you know, to some degree neither here nor there. Let's talk about decimal places. Let's talk about the real numbers. So, in terms of the manner in which decimals are represented in the computer, it's, this is an error. This should be 10. There is a, you know, within the decimal system, you have a you know, a reasonably straightforward way of approaching the problem. When you have numbers on to the left of a decimal place, those numbers are positive powers of whatever the base is. And when you have digits to the right of the decimal place, those are negative powers of whatever the base is, starting at -1. So, when we have a 5 here, that's multiplied by 5 times 10 to the -1, which is, of course, 0.1. 3 times 10 to the -2, which is 0.03, etc., etc. That's how we represent That's how we represent fractional numbers. That's how we represent real numbers within the decimal system. Sure, so far, so elementary school. So here's how things work in binary. It is almost precisely the same thing. Within the binary system, we have these fractional numbers that exist. These fractional components that are also multiplied by 2 to the power of some negative exponent. So the first one is 0.5. The next one is 0.25. The next one is 0.125. The next one is 0.0625, etc., 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 etc. Each one of these digits has to represent something that is divisible by some negative power of 2, right? So this is interesting, though, because this introduces certain restrictions. Here's a question. How do we represent 0.1 inside of a binary fractional number system? I have to be careful because normally we call fractional numbers decimals, but right now decimal means in base 10. So we have to distinguish, we have to differentiate our language at the moment. Once you're done with my class, you can go back to calling them decimals and decimal points and everything. Everything will be hunky-dory, but for the moment, these are real numbers and we're talking about fractional numbers. So if we are to represent 0.1, we can get closer and closer depending on how many decimal digits we allow ourselves. So if we allow ourselves binary digits. If we allow ourselves 3 binary digits, and we make those 0, 0, and 1, we have 1/8, which is 0.125. That's not 0.1, right? If we allow ourselves 2 extra digits, we can have 0.00011. So we've got a 2 to the negative 4 and 2 to the negative 5. That's 1/16 plus 1/32. That's 3/32. That's 0.9375. Notice that this is much closer to 0.1, but we're not quite there yet. If we allow ourselves an additional 4 digits, we can get as close as 0.099609375. 51 out of 512. So the question then becomes, how many digits do you require to represent the decimal number 0.1 in binary with absolute accuracy? And the answer is, you cannot. And this might be a problem. So think about it this way. If you have the number 1/3, right? 1/3. In decimal, that's an infinitely repeating series of 3s, right? Everybody knows this from any time that, people should have an intuitive knowledge of this from elementary school on their calculator. 1/3 is 0.33333333 in decimal. If you had a base 3 number system, you could represent that number in a finite series of trinary digits. However, because you're representing it in decimal, and that number does not resolve itself into a finite decimal representation, that's why you get all of 33333 all the way down to infinity. So the thing is, you have to, this is something to wrap your brain around. In the same way that a number, in the same way that 1/3 does not have a finite representation inside of the decimal system, there are decimal numbers that do not have finite representation within the binary system, right? So 0.1 is one of those numbers. And you can tell which one of these, you can tell whether or not a decimal number has a finite representation within the binary system by whether or not that, basically is this number expressible as some combination of base 2 fractions. If it's not expressible as a finite number of base 2 fractions, then it doesn't have finite representation within the binary system. Let me see if I haven't lost everybody. So, I mean, yeah, I guess I did make magnitude of a vector assumed knowledge, but then again, you did have to take high school math to get into, like, hypothetically, you should have taken at least grade 12 math to be taking this course in the first place. So, I stand by Pythagorean theorem as being assumed knowledge if you're taking this class. So, just like I would expect you to know what quadratic formula is. So, I'm going to skip the questions. But, which of 3/4 and 1/3 have finite binary representation? Obviously, it's 3/4 and not 1/3, because the base here, that's a power of 2. So that's expressible in things that are in negative powers of 2. Obviously. So here's the trick. We can actually view how Python is representing things under the hood using the format function. So let's take a standard number like 0.1. It just shows you 0.1, right? The thing is, it's not actually possible to have 0.1 with the degree of accuracy that's being shown to you represented inside of the computer system internally. What it's showing you is it's showing you an approximate or a rounded version of 0.1. That's why if you add 0.1 up 10 times, 6, 7, 8, 9, 10. 10 times 0.1 should be 1. But we do not get 1, we get 0.9999999, etc. So, the reason for that, format 0.1. This is called a format string. This is something that you would see in C, if you ever took a C class. So, notice that 0.1 is not 0.1. It is 0.00000, etc., all on down the line until we hit 555, 111, 51231, etc. It's off by a bit. Now, you know, this is a very small number within the number, right? Like, we're talking, you know, many orders of magnitude smaller than, you know, what any significant digit would be within this number, right? It's very small. It's very close. But it's not exact. And this is why equality doesn't work. So, if, for example, you wanted to do something like 0.1 plus 0.1 is equal to 0.2, you'd get true. But the closer you get, like the further you get from that, the less accurate that becomes, right? So why would 0.1 plus 0.1 equal 0.2, But 0.1 plus 0.1 plus 0.1 does not equal 0.3. It's because these errors have accumulated, right? The more operations that you perform on these numbers, the more these errors accumulate. And the more these errors accumulate, the more it's possible that your calculations will be thrown off. So the remedy to this is not to perform exact equality comparisons over floating point numbers. Don't do it. What you do is rather than performing exact equality comparisons, you subtract one from the other, take the absolute value, and test it to see if it's below a certain threshold. That works. And, that won't work if you have it slightly off. So the math works out for this, and you get to select the precision to which you are determining, whether or not it's true. Basically, what you're doing is you're turning the test from all of the bits in these two numbers must be precisely the same into these two numbers have to be close enough within a very, very small margin of error. And that margin of error should be so small as to think that both of these numbers are essentially the same. Although they may not be exactly the same because of the error that's introduced through floating point inaccuracy. This is floating point error or floating point inaccuracy. This is a fundamental law of computing. This is true for all computing languages. This is true for all computing systems. This is true when you enter a decimal number into a spreadsheet in Excel. This is universally true of computers. Period. This is the way they represent numbers. The reason that this is the way that they represent numbers is because this is actually the standard way that we handle decimal numbers. So there is an organization called the IEEE, which is, the International something Electrical Engineering, I think. The IEEE is the standards organization for the manner in which computers are put together. And they have a published standard on floating point representations of numbers. That means that it doesn't matter what computing device you're using, they will always be using the same type of representation for floating point numbers. It doesn't matter whether it's your computer, doesn't matter whether it's your phone, it doesn't matter whether it's your pocket calculator, it doesn't matter whether it's your Fitbit. They all perform floating point calculations in the same manner because it's been standardized by this standard, right? Okay, so with Python, only the first 16 decimal digits are given in standard output, right? So basically, for 0.1, this representation gets cut off somewhere around here. This stuff doesn't get shown. That's why we have to ask for it explicitly using the format function. Notice this has been converted to a string. So, just keep in mind, although it says it's one thing, it's actually a different thing. Cool. Let me see if we got any questions. Institute of Electrical and Electronics Engineers. Thank you. Oh. Hey, Mark. Yep. It's cool. So, I've already kind of talked about this, but when you perform these types of calculations... Oh man, my hands are dry. Ugh. Anyway, sorry. So when you perform these types of calculations, the errors will accumulate the more operations you perform. So that's why with this, 0.1 plus 0.2, you get 0.2, like equality works in this case. but equality does not work in this case. It also probably has to do with the idea of doubling, right? Doubling is a binary operation, so, that's probably why that works. So, the point, though, is that you don't know beforehand which cases you'll be able to use equality on and which cases you won't be able to use equality on, so you should never use equality over fractional numbers. Just never do it. Because, rare is the case where you will be performing equality comparisons over two literal values, right? Normally, there's at least one variable in there, right? So, variables, obviously, you don't know what the value's going to be. It's a variable, right? So you never know if equality is going to be a thing that'll be accurate over the types of numbers that you're dealing with, right? That's why you should always, always, always use inequality comparisons when you're using floating point numbers. So, and just to belabor this last point here, you can make the epsilon pretty small, but you can't make it infinitely small, right? So you can't... Yeah, see, there's a threshold somewhere in there, probably around 16, where this... Yeah, there we go. If you ask for too much precision, it'll still fail, because at that point you're basically... the interval, which is supposed to exclude the floating point error, does not exclude the floating point error because it's been made too small. It's been made smaller than the floating point error, therefore it won't smush it out of existence. So yeah. Anyway, long story short, you have to use inequality comparisons when you're trying to test for equality over floating point numbers, because the underlying representation is not necessarily accurate. Cool. So we've talked quite a bit about how I've talked about floating point numbers a lot, but you probably to this point don't even know why they're called floating point numbers. It's actually reasonably easy to understand, but it requires a little bit of brain work. So the way that the IEEE has decided to handle the issue of floating point numbers, while it is definitely possible to represent numbers in the manner in which we discussed on a previous slide, where you have some digits describing the number to the left of the decimal place, to the left of the point, and some of the digits describing the number to the right of it. Some are some digits representing the whole number component, some digits representing the partial number component. It turns out that doesn't, within the context of a 64-bit number, the question is, where do you decide where that decimal point should be, right? If you put it in the middle, then you can represent reasonably large numbers and you can represent reasonable precision, but your total range of numbers is quite limited, actually. So the solution that was that very intelligent people came up with to this problem is to essentially produce an implementation of scientific notation within computer systems. So rather than have the whole number component and the fractional component both represented in binary notation, what these floating point numbers do is they have all fractional component plus an exponent component. So the fractional component is technically termed the mantissa, and then you have the exponent component as well. That's called the exponent. No fancy name for it. So one of the optimizations that, like, one of the things that had to be decided way back in the 60s when these sorts of things were being standardized for the entire, like, this is a standard that will probably exist for the rest of human history, right? Because, nobody's going to it's like how QWERTY keyboards are probably going to be with us until the end of time now, because nobody is sufficiently like, it's so ingrained now that it's not worth the effort to change it, right? Same thing with these floating point representations. So a certain number of bits had to be allocated to the exponent, and a certain number of bits had to be allocated to the fractional component. And we had 64 bits to work with. So it turned out that what they decided to do was 52 bits will store the fraction. The exponent will be 11 bits, and then the remaining 1 bit will indicate whether it's positive or negative. And so that gives you a pretty big range. This means that the largest possible positive number that it's possible to represent inside a floating point representation is 0.79, etc., times 10 to the 308. And the smallest possible number is 2.225 times 10 to the negative 308. And, 10 to the 308 is like longer than the age of the universe in picoseconds or something, right? Like, that's a very, very, very large number. So they're kind of like, probably we won't need anything more than this. This is like a number that's larger than the number of atoms in the universe, right? So probably big enough. Higher even than my score on Pokemon Pinball. Ha. But, yeah. So this is the way that they've chosen to represent it. Let me see if there are any questions for me and not Mark. Nope. Okay. Cool. So, most computers follow the Ieee Standard on floating point computation. This is why, computer system... It's because these sorts of things are standardized that computers can talk to each other. Like an Acer can talk to a Toshiba, can talk to an Asus. They can all talk to each other because they all represent their numbers the same way, right? So, but here's an interesting thing, right? Well, actually, let me get to this first. So, the number of bits in the fractional component, that limits the precision, right? If you put more bits into the fraction, you can get more precision out of a number. If you take bits out of the fractional component and give them to other things, then you're losing precision. If you add bits to the exponent component, you increase the range of the number. And if you take bits away from the exponent, you reduce the range of the number. So, like, this 11 bits, 52 bits, this is the optimization that these engineers in the 60s came up with between range and precision. So there you go. Arithmetic operations on floating point numbers may lead to the loss of significant digits. So, just to take an example, if we have this integer number, we can perform this integer arithmetic. Nothing is lost, right? The arithmetic is performed accurately. Turn it into a float. Sorry, let me try it with a few more zeros. Yeah, let me try it with a few more zeros. There we go. So, if we make this number sufficiently large and floating point, adding numbers to it that are smaller than the precision of the floating point number will lead to inaccurate results, because basically these numbers get gobbled up by the representation. They are not significant enough to be kept by the representation. They don't enter into the framework, right? So they are dropped. They are lost. They are lost to history. There is no record kept of them. They are the ghosts of the computer. Cool. So, what if you want exact arithmetic, though? What if what if it's really important that these numbers be represented accurately? Well, you've got a couple of options. The decimal library hypothetically produces the same errors as calculations by hand. By default, 28 fractional digits are kept, and the precision can be adjusted. So the decimal library, if you enter numbers into decimal, then those numbers keep their precision. So if we import from decimal, did I do that? Sorry. From decimal, import decimal. Decimal of 1 divided by decimal 3 is decimal. See, it's keeping more precision. That's just more precision than you would get with floating point numbers. Furthermore, in the decimal library, you know, things work the way that you would expect them to if you were doing the calculation by hand in decimal, right? You have to be careful, though, because if you enter in a floating point number using decimal, then it'll just keep the representation, right? So, because this number came with this baggage when we gave it to the decimal library, it will keep that baggage. So the way that you represent these numbers accurately is you actually make them a string, and then decimal will interpret them correctly. So that's how you use the decimal number, the decimal library. So, okay, so why doesn't everybody just use this? Well, because it's much slower. Much, much slower. So the thing about floating point operations is that because they've existed for so long, all the CPUs that exist in the modern context have dedicated circuits that are built specifically for accelerating floating point operations. They have hardware native, like they're native to the hardware you're running on. The decimal library in Python is not native to the hardware that you're writing on because it's software, it's not hardware. Because it's in software and not hardware, it's much slower. So, while the decimal library can be used effectively to defray floating point error when that needs to occur, you're going to pay a penalty for it in runtime. For the purposes of your assignment, that's probably not going to be even visible, right? Because your assignment questions, and, you know, the types of programs you would run, you would produce in an educational context, these are probably not going to be having sufficiently stringent runtime requirements that this is going to be a noticeable problem. But in, take, for example, rendering engine for a video game, right? Those things do actually push the computer's resource limits, right? So, if you used a representation for decimal numbers that takes, 3 times as long to calculate as a regular floating point number, or more, that would result in a, a 1/3, like your engine's run speed would dip by 1/3 of what it should be, which is problematic because, that would have a serious effect on the ability of your program to render Crysis 2 or Skyrims. So, yeah. These things, there are domains in which this stuff actually has an effect. Because within a game engine, many of the values that you'll be dealing with are floating point values rather than integer values. So yeah, another library that you can use that can speed things up is the rational is a number for rational numbers, fraction, the fraction library. So from fractions, import fraction. So this is basically a representation that allows you to do fractional numbers without losing precision. So it's kind of like sidestepping the decimal system entirely and just working in fractions. So 1 divided by fraction 3, fraction 1, 3. So rather than representing it as a decimal, it just gives you the top, it gives you the bottom, right? So fraction 1, 3 times fraction 7, 24 is fraction 7, 72, right? It's just fraction arithmetic. Just take this comma and imagine it as the, you know, the fraction line. I don't know what you even call that. The line between the numerator and the denominator. And that's what you get. Yep. So, this is also a possibility. It makes certain types of calculations more precise. If it, you know, if you're dealing with sort of native fractional problems, then it might be of advantage to use the fraction library. You know, it's sort of, that's also an option for you. So, how do we deal with floating point numbers then? Well, the first thing you can do is just try to avoid them entirely. If you remember our make change problem, you know, cents are, like, if you represent money in terms of dollars and fractions of dollars being cents, then you have to involve floating point representation. However, if you consider cents to be the base unit, then you don't have to involve floating point. You can do everything in integer arithmetic. So one of the ways to avoid floating point problems is by not using floating point wherever possible. So that means doing cents rather than dollars and millimeters rather than meters. You can also use decimal fractions standard libraries. They are slower, particularly for larger small numbers, but they represent more accuracy. You can use a library for interval arithmetic with float. It gives safe lower and upper bounds, but it takes twice as much memory or time. You can use a problem-specific library, or check literature for algorithms with known numerical properties. So, if you're solving differential equations, use a library for solving differential equations. Use symbolic computation, as in computer algebra systems, instead of a programming language. So, use MATLAB, or something like it. When using float, never compare for equality. Check result within a tolerance. If you take nothing else, take number 6. Cool. Checking for questions. Yeah. So, it's kind of like, think back to the 70s, right? Or think back to the 70s and 80s. Oh. Yeah, it's like, okay, you know, if you have a country that's hypothetically, you know, not within the world trading bloc, or however you want to phrase that, like, okay, sure, but, you know, where are you going to get your computer chips, you know? It's like that, that joke in that one movie about space and spaceships, where I think it's, like Armageddon, where like the comet, they have to defray a comet that's going to impact the Earth. Anyway, it's like, this person's like, American parts, Russian parts, all made in Taiwan. And that's actually the situation. But yeah, yeah, that's, you know, never underestimate the power of standardization. all of you people, well, I would say, like, if you guys were in the engineering program, I would give you guys a quick, finger wagging about how following standards is the only thing that holds up human civilization. But you guys are computer scientists, not in the engineering program, and well, actually, you guys aren't even computer scientists. You guys, well, like 2 of you guys are computer scientists. Normally, if I was teaching an engineering class, I would go off on standards for a little bit, but just to have an appreciation for standards, because, like, honestly, if the entirety of human civilization were to collapse in on itself like a souffle, and just the standards documents were left over, civilization could be rebuilt from just the standards documents. That's, like, yeah. Anyway. Yeah, anyway, so that's class. Hopefully y'all learned something today. What are we talking about here? Oh, yeah, so the next bit is more algorithm stuff. So, cool. Yep. Well, think about it this way, right? Okay, so in Hamilton, there is there's a museum in Hamilton that's actually not too far from my house called the Steam Museum, and it's very, very interesting. Essentially, what this museum is Hamilton was one of the first places in North America to have a steam-driven water pump to supply water to the city, right? So they have this, like, great big steam engine that looks like a it looks a little bit like an oil derrick, actually, that they use to pump oil out of the ground. You've seen pictures of these things from Alberta, but they got this great big steam engine that's inside of this beautiful, beautiful brick building. And, if any of you are ever in Hamilton, I highly recommend going and taking a look at this thing, because it's just a beautiful piece of engineering. However, you should also appreciate it as, like, if you don't know what you're doing and servicing this thing, you will easily lose fingers. Like, easiest thing in the world to lose fingers. But, one of the interesting things about this is that every single nut and bolt in that entire apparatus, like, every nut belongs to one bolt because they were made for each other by a blacksmith. These are not standardized parts. So you have to keep track of which bolt belongs to which nut, or else, like, you'll spend the entire day trying to, swap them around to see if you can remember which one belongs to which one, because they're not standardized. Whereas on any modern piece of equipment, the bolt sizes will be standardized. So, like, it doesn't matter which bolt you put the nut on, as long as all of the nuts end up on some bolt, it all works, right? But yeah, that's the power of standardization. Imagine a world where, like, every screw in your house had slightly different dimensions. It's amazing. Amazing to think about. Yeah, who do you think used to make these steam engines? Blacksmiths. Yes. I mean, well, yeah, there would have been a certain amount of blacksmithing going on. Like, you would use different processes to make different things, right? Like, a lot of the parts would be cast, right? Cast iron. There was a trade of, cast making. metal casting was a trade, right? Actually, one of my grand uncles, something like that, someone in my family, their profession was they made the wooden models that were then used to cast metal parts. So you would make the thing in wood, you would then make a sand mold of it, and then you would pour molten iron into it and make the part, and some of these parts were very large, right? So you can imagine, like the main beam of this steam engine probably goes from one corner of my house to the other, and it's all one solid cast part, right? But yeah, but a lot of the parts in that thing, especially like anything that's fiddly, like a hinge or a screw or something like that, that would likely have been made by a guy on an anvil, right? This was before machining. This was before CNC machines, Absolutely. Yeah. Like if you go into some of the manufacturing labs in JHE, they still got anvils. Anvils are still a thing. But primarily, like, most of it these days are computerized CNC machines because they're more accurate than human beings and they're also more repeatable than human beings, right? But yeah, don't underestimate your good old blacksmith. Like, I'm pretty sure horseshoes are still done by smiths. And certainly you have to, like, you would need a blacksmith to install horseshoes, I think. But yeah, anyway. Sure, okay, yeah. Screws are made with twisting, not banging. Sure, okay. But, okay. I'm using the hammer and anvil as a stand-in for all blacksmith tools, right? Like, obviously, like, even something like a screw, like, you would need a specialized thing to make a screw. But, yeah, I'm speaking in generalities. I think, like, I saw on YouTube once, there was this really cool video of a guy, like a blacksmith's shop from the 1950s in Germany. And it was interesting because, like, he's, like, pulling on levers and, like, he's got machines and it's all very cool. But anyway. That's your prof simping for blacksmiths. It's cool. It's a cool profession. If I were living in, like, medieval Europe, I would aspire to become a blacksmith. Blacksmith or masonry. Masonry is also a really, really cool trade. Like, very, very neat. But, probably I would have just been a peasant. Because, most people back then were peasants, so, That's okay. I also like growing cabbages. Growing cabbages is also fun. Someone's got to grow the cabbages, Anyway. Anywho, I guess, There are many memorial places in Germany with blacksmithing features. Yes. Well, Germany takes its trades very, very seriously. Like, I'm pretty like I believe I have a friend who's German, and I think he did his high school in Germany, and I think I remember him telling me at some point that, like, if you're in high school in Germany, it doesn't matter who you are, you get trained in some trade or another. Because, the idea is that you should be useful, So, Yeah, no, masonry and blacksmithing are completely different things. Masonry is it's stoneworking, right? You have to cut stone blocks so that they can be built into an archway, and that archway lasts for 500 years. It's really, really cool. Yeah, masonry is stonework, yeah. But yeah, like a few years ago, when my wife and I were on our when we were on our honeymoon, we decided to go to Barcelona because we had our wedding in February. So we were like, I would love to visit like Sweden, but not in February, February, you want to stay closer to the Mediterranean, and we wanted to see culture, right? Oh, is it possible to talk with me after class briefly about a private matter? Yes. Yeah, we'll shoot me an email. We'll set up a Teams something. Okay. Well, not shoot me an email. Contact me on Teams and send me a private message on Teams, and we'll sort something out for sure. Yeah. So, oh, you used to be a stonemason? That's so cool. Yeah. Like, masonry is like one of those professions that it's like, there's still a certain amount of call for it, and it's a profession that hasn't, it's still fundamentally the same thing as it was in the medieval period, Fundamentally, you've got stones, and you need to fit them together in order to have a thing that doesn't fall down, But anyway, we were in Barcelona, and it's just incredible to see city walls of the old city of Barcelona. Because, Barcelona it was originally a Roman colony, right? So the or it was it was a village that was then turned into a Roman colony at some point during the height of the Empire. The Roman Empire. So they built city walls. It's actually a reasonably strategic point in the Mediterranean, right? And these city walls have literally been standing since the 2nd century. And you can tell because the stone looks old, right? But it's still standing. It's been repaired in places. And you can see where they've, you can see in where in the 15th century they had to add some more stones in particular places and such. But one of the really interesting things about the difference between the the Renaissance and medieval parts of the wall versus the original Roman parts of the wall is that when the original Roman parts you could tell that was made with slave labor, because the stones are the size of people. It would have taken 10 people to move one of these stones. It's absolutely incredible. But, yeah. So, it's oh, what did you like? What did you like about your vacation? Was it the food? Was it the, was it the beach? Did you go to the beach? No, I looked at a brick wall, It was really cool. It was a really old brick wall. It wasn't actually brick. It was a stone wall. But anyway, yeah, okay. So I'm gonna log off here. Probably most people have gone to their classes already. But, anyway, that's it. Thank you very much. Thank you for listening to me. Thank you for listening to your professor simp for blacksmiths and stonemasons. Take her easy, folks. I don't know. I've run out.